I'm going to talk about some nice combinatorial aspect called the distribution problem. So this nomenclature is not that popular, but let's motivate with this example. Suppose I have 9 chocolates, and let's keep it identical, indistinguishable, to be distributed to five distinct kids. So note the numbers here. I would say this number of people are here kids 5, and number of objects here identical chocolates is 9. So I want to count. So counting is one of the mainstay of combinatorics. I want to count the number of ways in which I can distribute these 9 chocolates to 5 kids. So this is understood by a popular strategy called the strategy of dots and slashes. So what I mean by this is that let's say I would like to indicate this kind of a thing. The first kid received 3 chocolates, the second kid received 3 chocolates, the third kid receives 3 chocolates, the fourth 1 chocolate, and fifth 0. So 0 is also allowed. The solutions are happening in non-negative integers. So how do I indicate this? I indicate this as three dots for the first kid, then followed by a slash, 3 dots for the second kid, followed by a slash, 3 dots for the third kid, followed by a slash, 1 dot for the fourth kid, and I don't put a slash because it is understood that the last is 0. So, or maybe I can put a slash here. So you can observe that all 10 chocolates have been represented here, 3, 3, 3, 1, but only 4 slashes I have. That means I need not put a last slash. So even for example, let's take another distribution. Let's say it could be 2, 2, 3, 2, and 1. So this is another. So this I can represent as 2 dots, a slash, 2 dots, a slash, 3 dots, slash, 2 dots, a slash, 1 dot. Now you see this last person doesn't get followed by a slash. So it's understood that this last is for the last kid. So that's why you get 1 less than the number of people. So if I say R is the number of people, N is the number of objects, then I would like to arrive at a combinatorial formula to solve the distribution problem. So basically, how many such representations are available? How many different combinations of these dots and slashes can be formed? So I would now want you all to understand that this representation can be understood in this way. Let's say I want to make a string with these 2 symbols, dots and slashes. So let's let's make a variation of that. Dots could be represented as zeros for dots and ones for the slashes. So basically, I'm looking at all kinds of strings, with n number of dots or zeros and r minus 1. Remember, I said the slashes are 1 less than the total number of people. So r minus 1 number of ones. So each of my representation may look like, for example, that 331 could look like 0 0 0 1 0 0 0 1 0 0 0 1. So yeah, one more, that one last dot is mentioned. So this is a string of 10 zeros, and did I make a mistake? Yeah, there should be one here. There should be one here. So this is 10 zeros and 4 ones, right? So basically you have 14 symbols. So you've seen in the course on permutations and combinations that this is exactly like in how many ways can you arrange the symbols or letters of a certain word. And my word here is consisting of 10 zeros and 4 ones. So which means you generally do it as 14 factorial divided by, because these are indistinguishable, I would put a 10 factorial here and put a 4 factorial. So whenever there are identical letters in your word, you put those things, right? So this is a very standard way of understanding the number of ways in which you can permute these symbols. So this, in more generality, how would I say it? It is n plus r minus 1 factorial divided by n factorial to r minus factorial, because you had r minus 1 slashes n number of dots, or r minus 1 ones and number of zeros. So you're arranging a string basically. So now you quickly see that this is exactly the formula for n plus r minus 1 choose n. If you want to know in this way, it's combinations with n plus r minus 1 symbols, n chosen at a time. Same written as n plus r minus 1 c n. Right? So this is the formula to distribute n number of indistinguishable objects to r people. So this in combinatorics books, it is written under the title of combinations with repetitions. So I kind of gave a proof for why it can be captured by n plus r minus 1 choose n number of ways. So I want to end this short talk by looking at kind of a Diophantine problem. You have a Diophantine problem, as you know, as in the honor of Diophantus, a Greek mathematician. So who looked at who wanted integer solutions to certain polynomial equations. So here I have a linear polynomial equation in 3 variables. Let's say, sorry, this is z, x plus y plus z equals 17, let's say. I want to know the number of ways or number of solutions to this linear differential equation in non-negative integers. So which means I could have a solution like 14 plus 2 plus 1 equal to 7. This is one solution. So the triple 14, 2, 1 is a solution to this differential equation. So in the spirit of what I did earlier, as I said, the last kid was in the first solution, I said 0 chocolates. So like that, you could also give 0 to one of the variables or two of the variables. So 17 plus 0 plus 0 is also a solution. So it reminds us of the Ramanujan partition function kind of a thing. So you could as well have 16 plus 1 plus 0 as a solution, or 17 plus 0 plus 0 also as a solution. So how many such solutions are there? So now here I could put this problem uh, in the context of combinations with repetitions, or what I call distribution problems. So I want to distribute 17 units, which is there in the right hand side, to three variables x, y, z. So I'm distributing 17 units to three variables x, y, z. So the number of people here is, I mean, that's how I'm looking at the three guys. See, x, y, z have to be distributed with these 17 units. Is r, which is 3. The number of objects here is n, which is 17 units. So your required formula is n plus r minus 1 choose n, which is 17 plus 3, 20 minus 1, 19 choose 17, because we have 17 objects. So 19 choose 17, which is precisely 19C17. Let me do the calculation here. So what we have here is 19C17 equals 19 factorial by 19 minus 17 factorial into 17 factorial, which is 19 into 18 by 2, which is 19 into, all right, 19 into 18, 17 factorial is stuck. So it is 19 into 9, which is precisely 171. So there are 171 solutions to the differential problem in, mind you, non-negative integers. So usually differential problems are understood with either natural numbers or the whole of z, or sometimes with the rational numbers. But here I'm looking at over non-negative integers. My solutions are exactly 171. So that's it, guys. Thank you for watching this video.